I hope everyone can see the slides.
Yes.
All right. 1 second. Okay. Can everyone on Zoom hear me? And is everything good? Yeah.
Good. Yes.
Okay. All right, cool. Okay, I'm hoping everything's good. Yeah, I guess ping in the chat if there's any problems. But yeah, my name is Sudeep. I'm presenting this work called An Unbiased Look at Data Sets for Visual Motor Pre-Training. This is some stuff we did with collaborators at Meta and CMU, namely Mohan, Unat, and Abhinav. Oops. So just for a quick recap, there's been this paradigm shift recently towards doing pre-training representations on internet scale data and then transferring them to the real world. And the problem we're trying to solve is that even large scale robotics data sets, they may not cover your exact lab space, right? So, I mean, if you look at all the data and all the diversity that we can even collect in things like RT1, your specific lab may be still quite different, right? So one ideal is if we can use out-of-domain data, the sort of billions and trillions of images that are constantly being uploaded to the internet, use that diversity to try and learn effective visual representations that we can then transfer into a robotic setting. And this kind of raises an important question. What data should we be using for this pre-training process? So far, the field has sort of settled on an answer of Eagle4D, right? Prior work, be it MVP or R3M or VC1, they really focused on trying to use this in the wild data from Eagle4D. And the reason for this is because, first off, the data set is large. It has 3,000 plus hours of footage. It's targeted to human manipulation behaviors. And it's in the real world, right? It has these in the wild video sequences. And we want our robots to work in the wild. So hopefully this in the wild setup would be ideal for robotics. But are these assumptions actually correct? Or is this just something that the field has taken for granted? So test this, we pre-train representations on 5 data sets, including Eagle4D and ImageNet, 100 Days of Hands, RoboNet, which is a robotics data set, and Kinetics, which is from the vision community. And we take these data sets, 1 million frames from each, and we pre-train a masked autoencoder algorithm on it, which we then fine-tune to downstream sim and robotics tasks using behavior cloning. There's a lot of emphasis we place on the real-world evaluation. So to be very clear here, we have these 3 tasks: stacking, pouring, and toasting. They all have novel objects and novel configurations, and every policy is learned using 50 teleop demos. So the fine-tuning stack really is trying to leverage the strength of the representation to make this sort of data-efficient BC setup work effectively. And one of the key results that we find from our study is that these assumptions are not valid. So again, we're comparing these data sets in an apples-to-apples comparison with 1 million frames from each data set. And we find that these old-school curated vision data sets like ImageNet, Kinetics, and 100 Days of Hands are actually better for visual motor pre-training than either Eagle4D or RoboNet were. And in fact, these vision data sets outperform some of the state-of-the-art baselines like VC1 and MVP that we mentioned earlier that actually kind of got this trend rolling. And there's this really fascinating thing here where the baselines, for example, VC1 actually included ImageNet data as part of its pre-training. It's trained on ImageNet combined with millions of extra frames. So how is it still able to underperform? One key idea that we found is important is that the distribution of the data, not just the sheer amount, actually matters a lot. So for example, if you look at the if you look at VC1's batches, the distribution of the data in each batch seen during pre-training, it's skewed heavily towards Eagle4D. And it's skewed away, like the average batch sees very little of ImageNet and the other vision data sets. So we come up with a very simple idea to try and fix this issue. What if we could boost the diversity of the batches simply by unskewing the data? So by using some amount of ImageNet, some amount of Eagle4D, and then also balancing the rest of the, just sampling a lot of other data sets, and then balancing the rest of the batch with those, we can actually create an unskewed version of the pre-training set that's way stronger and way more diverse. And I think the key insight here is that the data distribution matters a lot, and the diversity of that distribution matters, right? Because if you think about what is visual motor pre-training, it's actually essentially a compression task. So you want to have a pretext, make that pretext task as challenging as possible, and force the encoder to represent all different types of data rather than just sort of the simpler scenes that you may see in a data set like Eagle4D. So one reason why, one sort of interesting thing we found is that if you do this evaluation purely in simulation, right? Like we mentioned, we had some real world tasks and some sim tasks, but if you do the evaluation purely in sim, you don't find the same trends. So here we're plotting the average performance in the simulator against the average performance in the real world. And we find very, very little correlation between the numbers that are calculated in sim and the numbers calculated in real. And this is true even when comparing just the simplest task possible. So we have a block stacking task in simulation, and then we have the block stacking task in the real world. And we find there's actually very little correlation between the numbers from sim and the numbers in our real environment. So I think this have sort of three important takeaways from this work, namely that data is critical when doing visual motor pre-training. And while we have a lot of notions and preconceptions about how data may be useful for robotics, we actually don't know what the right answer is right now. And it's actually quite damaging to just assume that we should just have more in the wild data or data from a specific form factor. Another idea that we found is really important is that boosting diversity and creating a broader image distribution during pre-training can actually improve transfer quite dramatically when doing robotics tasks. And our final thing is that sim eval alone can be quite misleading. And if you want to make sure that your results are correct in sim, you have to evaluate both in a bunch of different settings, like essentially change the sim environment during testing so that there's some degree of transfer. And you also have to do like some testing in the real world to make sure things are valid. Yeah, I've got a few minutes open for questions if there are any.
Thanks. Yes.
So like getting robot data is pretty hard, right? Because
Mhm.
the setup can be kind of complicated and it takes time to debug the hardware, a lot of the kind of stuff like that. So
Mhm.
do you think this is where like LLMs can come in, where they kind of pass on common sense knowledge to robots, and the data collection in that setting is a lot easier, and then we kind of just use that as a warp start before we perform tasks?
I think that approach could have a lot of benefit when doing things like decomposing tasks into simpler components that they can solve. But right, but for like I think some of the basic manipulation behaviors, like how do you pick something, how do you place something, how do you grasp? I'm not necessarily sure that language decomposition will be that helpful in those sort of like when it comes to the basics of manipulation.
I see, so you think it's better for long driving tasks, but not for learning.
Yeah, I guess the claim I'll make is I'm not necessarily sure how just an LLM decomposition or like task suggestion by itself can help with things like how do I grasp a cup better, right?
Because like for me, it's just that with the data collection, it's quite difficult to get large data sets
Mhm.
with robots unless you have a big effort across many institutions like RTX.
Right.
So that's just how, so I'm not clear, like what do you think is the best way to improve like data?
Yeah, so the point of this is to show that like if you want to do pre-training or from a visual angle, right? So using out of domain data and then transferring it to a robotic setting. It's not enough to just take data like in the wild data like Eagle4D or just like hyper focus on like specific data sets. You should create as much diversity in the pre-training data set as possible. And that means that you shouldn't essentially you shouldn't necessarily like have strong assumptions about what that pre-training data set should look like. You should actually like run these evaluations and study like how do we like boost the diversity during the pre-training and then like bring in like enough interesting data that the robot can actually learn good representations from.
One other question. I was wondering how do you structure your evaluation set? That There's some recent work which compared RTM versus like just fine-tuning a behavior learning model from scratch, right? And they can show superior performance, and I don't necessarily believe that it leads to superior performance, but is it based on evaluation setup? Do you see good thing, or do you think it's just an artifact of ego coding?
So yeah, that particular paper, I believe. Okay, I'm not sure what happened to Zoom there. That particular paper, I believe, showed the superior performance thanks to using data augmentation. I assume the paper you're referencing is like the from scratch baseline, right?
I think I've seen it in multiple papers recently. Like a lot of papers have reported that Artham does not give good performance, and they try to do data cloning from scratch. So I'm not talking about anything.
Right. So the papers I'm aware of, they use better experimental setups. So they do things like data augmentation during behavior cloning, or like essentially like better regularization during behavior cloning. And we actually adopt those best practices as part of our setup. So when we do our BC fine tuning, it does actually do data augmentation. And we do have additional experiments in the paper where we show that things like the augmentation and like dropout regularization, even like simple tricks like this can boost performance and can actually change the numbers a bit. So I'm not entirely sure the exact papers you're discussing, so I can't say like in disambiguation, right? But I can tell you roughly that we like investigated, like trying to get a stronger setup.
This data augmentation versus the pre-training data. What do you think is more important?
I think the pre-training data is more important from our current experiments.
In the interest of time, let's thank the speaker and move on to the speaker.
Next up, we have CEO.
Okay, cool. So let me get started. So yeah, my name is Shuo Chen, and I'm a PhD student in the IL2 lab at Georgia Tech. And today I will talk about scalable and generalizable robot skill representations for long horizon manipulation. And specifically, I will talk about two works that focus on this topic. So okay, so yeah, so before I start, I would like to ask the question, why is skill learning important? So my understanding to this question is daily tasks are usually long horizon, and the different tasks and domains may require using similar skills. So what are the challenges for robot skill learning? Suppose you have the robot in the kitchen and you want it to clean up the table for you. The robot faces two challenges. The scalability, which means the robot needs to acquire a bunch of skills in a very efficient way, and generalizability, which means the robot needs to handle very diverse objects, appearance, colors, lightings, and poses. So I argue that for solving the scalability issue, the robots need to develop and adapt their skills in a continuous way. And the learning every skill from scratch leads to unnecessary redundancy and inefficiency. And for the generalizability, the robot needed to acquire the capability of handling diverse objects, poses, goal configurations with small amount of training data. Because in real world, collecting robot data is really expensive. So previous works for this question can be mainly grouped into two categories: task and motion planning, which can handle long horizon goals very well, but they require knowing object models and cannot handle context-rich tasks very well. And hierarchical reinforcement learning or imitation learning, which do not require object models and can handle context-rich tasks, but they cannot handle long horizon goals very well and do not generalize well to new poses and geometries. So by combining the benefits of task and the motion planning and the reinforcement learning, we developed the league system. So in this work, we aim to answer the following questions. Can we build an agent to learn skills efficiently and continuously to solve new tasks? and what kind of state and action representation allow us to reuse the learned skills in new tasks and domains. So our system allows us to progressively acquire new skills in situ of task and motion planning, and it allows us to efficiently learn reusable skills through symbolic abstraction. So specifically, our framework starts with a group of defined symbolic operators and a library of randomly initialized skill policies. And given a task goal, we generate symbolic task plan to invoke corresponding skill policies for execution. And the failed skills will be recorded for further exploration and learning. And to improve the failed skills, we leverage symbolic operators to extract the state of target objects and use the desired effects to generate the reward, yielding a skill-relevant state space and an operator-guided reward function. So the improved skills will be automatically integrated into the framework for accelerating the learning of new skills. And this process is repeated until all the necessary skills are mastered and the task is solved. And our learned skills support reuse across task goals and domains. So here is the visualization of the skill learning process. We can see that our framework will continuously improve all necessary skills in a sequential way until finally the task is solved. And we show that our learned skills can be directly composed to solve new task goals. And we also show that the skills learned in one task domain can be directly reduced to warm start the learning of a new task domain. And here we show the execution in the real world of our full system. So far we've talked about how to scale up skill acquisition, but how can we generalize individual skills? So we know that daily objects have diverse shapes, appearance, and lightings. So we ask the following questions. What kind of representation enables us to generalize the skills? And can we achieve rapid skill acquisition in a more sample efficient way? So one noticeable recent work is called neural descript field, which provides strong generalization over diverse shapes and poses, but it is only limited to short horizon tasks. So by combining the benefits of task and motion planning and the neural object descriptors, we developed the node camp system. So we aim to answer the following questions. How can we inherit the strong generalization over geometries and poses from neural object descriptors? And how can we chain up the skills to reach long-term goals? And how can we leverage existing TAM system to accelerate the manipulation process? So our system allows us to acquire new skills rapidly through just a few demonstrations. And our system composes the skills to solve long horizon goals and is showing strong generalization over shapes and poses and goals. So to generalize each demonstrated skill, we use the learned neural object descriptors to transfer the recorded demo trajectory through the test scene. And we also realized that same skill category may have different manipulating styles. For example, for the placement skill, we may choose to place the mark in a side way, or we can like place the mark into the bin through the top-down way. So we asked the question, how can we chain up the skills and ensure the compatibility? Because the style of the place skill may depend on how we grasp the mark. So we propose to chain up skills with neural object descriptors, since the neural object descriptors can be used to measure the relationship between objects. So we compute the distance of the neural object descriptor feature for each paired skill and to measure whether two skills are compatible or not. And here is the overview of our full system. So given the task goal specification and a small set of short skill demonstrations, we first generate the symbolic task plan with the task planner. And then we use the skill training module to select the relevant demonstration skills and place them in the correct order. And then we use the trajectory adaptation module to transfer each selected skill to the test scene for execution. So by providing just two scale trajectories with one mark instance, our system can solve a wide range of tasks with diverse shapes, poses, and goal configurations. And here is the visualization of the execution process in simulation. And here is the visualization of the execution in real world. Okay, so to summarize the works, we developed a league system, which allows us to continuously and efficiently learn reusable skills. And we developed node temp system, which can repurpose brief demonstrations for solving long horizon tasks and generalize quite well to new geometries and configurations. And for future works, I believe that the symbiotic relationship between data and algorithm is super important for robot learning. On one hand, large-scale, high-quality data allow us to learn better components. And on the other hand, the improved algorithms allow us to enhance the efficiency for collecting new high-quality data. And the representation would affect the modality of what kind of data we can explore and how we can interpret the data. And it will also affect what kind of knowledge we can extract from the data and how can we generalize the components to new situations. So that would be all for my talk. Thank you all for your attention.
We'll take a quick couple of questions.
Yeah, please.
So for the grasping, that's sort of part of the skill, or you have some grasping module using
The grasping, the grasping strategy is provided through the reference demo. So the reference demo contains a sequence of any effective pose. So actually, you know how the gripper is approaching towards the object. So yeah.
Okay, thank you, Shiv.
Yeah, thank you.
I think up next would be Ankit Goyal. Ankit currently works at Research.
Okay. Yeah, hi everyone. So I'll be presenting our RVT, Robotic View Transformer for 3D Object Manipulation. So this work was done at the Seattle Robotics Lab of NVIDIA and with awesome folks like Jeshu, Ichigo, Vals, Yue Chao, and Dieter Fox. So before I go into the method, so here we are focusing on the 3D vision. Refer them as 3D management because they like drawers, screwing a bulb, placing things on the 3D surface, hanging cups. So this is a fundamental task in robot manipulation here. And here we are focusing on building one model that can solve many different tasks with language conditioned goal input. When I think about this problem, so we generally categorize the popular approaches into two categories. So first is view-based methods, and some examples are I4 and transporter net. So these methods are generally very scalable because they are just operating on the input images. But we find that they are generally not suitable for handling like 3D manipulation, or they are not made for handling 3D manipulation. On the other hand, there are these approaches which first construct an explicit 3D representation of the scene and then reason over these representations, especially voxels. And two of the common methods are perceiver actor and C2F arm. So they tend to perform much better on these tasks. But since these methods are consuming voxels, and as we know, voxels scale as cubic to the input resolution, these methods have to take in a lot of these pixels and process them, and so they don't really scale that well and require a lot of compute for training, which makes them not suitable if you want to try them for like large scale data sets. So since these explicit methods rely on voxels, the question we asked is, can we avoid this kind of processing and still get the performance? So the key idea of our work is that maybe instead of using voxels, maybe we can represent the scene through a set of views. And these views need not be like explicit views. So these could be like virtual views of the scene, and can we work with those? And here, we propose RVT, and we find that this is much more scalable and performs much better than what existed before. So I'll now go into the pipeline of RVT and try to explain what are like the key ingredients and some key insights. So the input, as I said, the input is language instruction and a scene. From the scene we get like input RGBD images, right? So these could come from like different cameras that are placed around the robot, and these could be moving. For example, these could come from the wrist. So this is like a very generic input pipeline. The first step is similar to explicit representation. So we build this explicit point cloud out of the provided input RGBD images. What we do differently is that we use these virtual cameras which are placed at fixed location with respect to the robot. And these virtual cameras are placed in orthogonal angles to capture some inductive biases. For example, there's the virtual camera could be placed right on top of the robot while there is no real camera there, or the virtual camera could be placed right in front of the robot while there is no real camera there. And since these are fixed with respect to the robot, they don't move even if the input images are moving around. So once we have these virtual images, we have our multi-view transformer model, which gives us a heat map location for each of the corresponding virtual images. So this is predicted by a generic multi-view transformer model. And what these locations indicate are the next end effector end effector location. So you can see like these end effector locations can be multimodal. For example, here is stacked teal blocks. So there are multiple blocks, and we get like this multimodal distribution from the top view. Once we have these heat maps, we project these heat maps to get a distribution over the 3D heat map. So essentially, you see that there are points in the 3D space which have like higher values. So this is simple projection operation, which is taking these values from the 2D heat maps and projecting it into 3D. from the predicted heat map locations, we sample or take the max location and execute and pass that to a motion policy, pass that to a motion policy which executes the policy. This new state is then updated, and the same step repeats itself till a terminal condition. So we find that in simulations with RVT, we could get much higher performance and as well as training speed, as well as inference speed and simulation results on RL bench. What we also find is that even in the real world, the simple method works really well. So here I'm showing multiple tasks where the same method uses just 10 demos, and it could do multiple different tasks while taking language input. And we get a decent success rate with some failure modes, as I show here. Like some of the key ideas in RVTs are like, one could ask, okay, why don't you use directly the input images instead of using this virtual orthographic images? And we see like a huge difference in performance. And also there are like inductive biases. For example, for the same input image, we could construct multiple different virtual images by just applying 3D augmentation on the point cloud, which is not possible to directly apply on the images. So we find a huge performance difference. Another key insight was that, okay, we could either use perspective projection or we could use orthographic projection. And we find that orthographic virtual projections tend to work much better. Another thing is like, we provide additional channels which give information of like point correspondence, and also that seems to help. Okay, so I'll summarize. So RVT is a general method for 3D object manipulation. It is trying to solve the scalability problem with explicit 3D methods by using these virtual views. And it works well in the real world with just 10 demos, and a single model can do multiple tasks. Thank you, and we'll be happy to take any questions.
Yeah, please go ahead.
So the example you show is with these blocks, these are vision objects. They give pretty strong like color cues.
Mhm.
But what if you didn't have like strong color cue? How would this work? And two, how does this work with deformable objects? Have you tried that at all?
Yeah, so here we don't do this. So mostly all these tasks have like articulated and rigid body objects. And with color cues, I think it's the same for all the methods would either benefit or will suffer with the lack of it. So it's not very specific to any particular method, I would say. So
Only tested in sim.
no, it was also tested in real.
Okay.
Yeah.
So this picture here is just like the sim environment.
Yeah.
But... And on more complex tasks, how does it work?
Yeah, so there are like this suite of tasks which involve like opening drawers, like doing other stuff like hanging cups and things like that. So there is very degree of success across all these tasks. Yeah.
Thank you for your talk. So I understand that going from a voxel representation to 2D representation improves inference speed and training speed. But do you have any intuition for what actually causes the better performance?
Yeah, there are multiple things. I think one is that for the same compute, now you could use higher resolution, and that improves performance. And
discretization. going from voxels.
Yeah. Going from voxels to the pixels, so you could have higher resolution. And also, I would say maybe since we have these orthographic projections and things like that, they are probably easier to learn. Yeah, so it's a combination of multiple factors.
Yeah, I think really cool work. I like that the premise of the work that you have this point of representation, and obviously having these different views virtually can project it to be. I was thinking about, obviously you will have faster inference. Why do you think your method also have better performance compared to the 3D point cloud method? Because I feel there's a natural trade-off between performance and inference here.
Yeah. So I think like the same as I said, because you could now have like higher resolution. And also I think like the other thing is like if something trains faster, is more scalable, you can train it more with the same compute.
Okay, thank you again.
Oops. Okay, good. Okay, hi everyone. I'm Zhen Xiang from UT Austin. I'm working with Professor Yuke Zhu, and I'm glad to present our work named Doodle, Learning Dense Visual Correspondence from Unsupervised Semantic Aware Flow here. Okay, so dense visual correspondence is a problem of finding the corresponding pixel in a target image for any given pixel in a source image. One major solution to this problem is learning from a labeled dataset. However, supervised learning of dense visual correspondence has limited generalizability for non-rigid transformation because this data, the dataset are usually labeled on those like a different image capturing the same rigid scene. And in this project, we studied the problem of unsupervised correspondence learning, which is more generalizable and scalable. And we learn from in-the-wild videos because these videos contains natural and diverse variations. And from this video, we learn our model, we call it Doodle, which takes as input a pair of RGB images and produce a dense visual correspondence. Well, with this model, we demonstrate multiple robotic applications that is enabled by this model, such as dense tracking, where we can track each pixel like accurately through the process manipulation, and also articulation estimation, where we can establish articulation model of this articulated object based on the dense visual correspondence, as well as zero-shot goal condition manipulation, where we build the correspondence between the initial state and the goal state and use this correspondence to extract actions that manipulate the initial state into the goal state. Yeah. And two notable categories of existing works in unsupervised visual correspondence is first unsupervised optical flow, which produces optical flow and uses optical flow to warp one image to another and minimize the distance between the warped image and the other image. And this method provides very fine-grained pixel level supervision, but it's not very robust to appearance changes. The second one is self-supervised semantic feature. They learn a augmentation invariant semantic feature representation using techniques such as contrastive learning. They produce very robust semantic features, but they usually has a very coarse correspondence. So our method kind of combine the best of the both worlds. So given a pair of input and given a pair of source and target images, we use a pre-trained semantic feature encoder to extract semantic features. And then based on this, which already gives us a kind of coarse correspondence. And based on this, we predict the semantic aware flow, and we use flow to warp the target image and target feature and minimize the distance
between the source image and source feature and target image and source image and target image and the source feature and the warped target feature. So more specifically, our architecture is like this. So given a pair of source and target image, we use a transformer based architecture to extract this correspondence-aware features of both images and compute cost volume based on the feature similarity. And then we use a semantic aware flow estimation module to estimate the flow between the pair of images. So this semantic aware flow estimation module is kind of core of the architecture. So first we use Dino, a pre-trained feature encoder, to extract semantic features of both images. And then for each point in the source image, we use this semantic feature similarity to extract these matching candidates. So basically for one point on source feature, we find the point in the target feature that has the closest semantic feature similarity to this point. So using this very nice, robust semantic feature, we can have a very nice, initial estimate of the, matching candidates. And using this property can help our network to focus, our trainable part to focus on the, on the fine-grained correspondence, and also reduce our computation burden because we only need to find the corresponding point in these mask candidates. And then we use mask softmax to estimate flow from the cost volume conditioning on this mask candidate, matching candidate mask. And then with this predicted flow, we warp the target image and target feature, and the correct flow should warp the target image to the source image and target feature to the source feature. So we minimize the distance between the warped image and source image and the warped feature and source feature, and use this loss to train our network. However, there is an issue because during our training, we deliberately use frames that are not very similar to each other to enhance the robustness of our correspondence. So this leads to a problem that a lot of pixels that are visible in the source frame are occluded in the target frame, and applying losses on these pixels harm the performance. Therefore, we introduce a visible region discovery technique where we first extract max similarity map from cost volume. Basically, it means like the possibility that the point in the source image is matched in the target image. And then we use off-the-shelf segmentation model to extract this instance masks from the source image, and we select masks with the highest maximum similarity and use this mask as a loss mask. So this is actually a bootstrapping strategy because the better our correspondence model is, the better the cost volume and the more accurate the maximum similarity map, and this leads to better loss mask, and which in turn help the training of the correspondence model. So this is a full training pipeline where we use this mask loss to train our network. And this whole training pipeline together with the semantic aware flow estimation can give us a robust and fine-grained correspondence. And then I'm going to demonstrate a few applications enabled by this general correspondence model. So mention all the results shown here are from the same model. So there's no fine-tuning on specific data sets because we are trained fully unsupervisedly. So first is dense tracking, where we use our model to extract the correspondence between the first frame and each following frame, and we visualize the corresponding feature using PCA. So we can see these features are pretty consistent during the process of manipulation, and also like this natural like deformation. And second, as I showed, that articulation estimation. So given a pair of images before and after the interaction of the articulated object, we establish this dense correspondence. And then we back project the dense correspondence to 3D, so we get 3D correspondence. And then we use directly a least square algorithm to estimate the articulation axis of these articulated models. So we never train any like data set with ground truth articulation axis. We just estimate it. It's a bottom-up solution, and we can see it's pretty accurate because the green on the bottom row, the green one is the ground truth, and the red one is our predicted ones. And lastly, this more interesting like manipulation is like we call it zero-shot goal condition manipulation. So basically, given a goal configuration and current configuration of the object, we first establish a dense correspondence, and then we extract action based on this correspondence. So basically, the action is like moving this point to the corresponding point, and then we execute this action. And after multiple rounds of correspondence estimation, action extraction, and execution, we can move the object from the initial state to the goal state. And we find this is pretty robust because we have multiple rounds of interactions. In summary, so we introduced Doodle, which learns correspondence from in-the-box videos without supervision, and it employs semantic-aware self-supervised flow training, which facilitates robust and fine-grained correspondence. And we show how this general correspondence model can enable multiple robotic applications. And everything is public on this QR code. You want to scan it. And please let me know if there's any questions. And thank you for listening.
We'll be able to take one quick question. Yes, please.
Do you have any results on if the object is common with and name is
Yeah, that's a good question. So yeah, so the prerequisite of establishing correspondence is there is correspondence. So if the object is like out of the scope, is in one frame in the source frame is inside and another frame is outside, then we cannot establish correspondence. But I do see that there's possibility of like using this correspondence to track and predict the trajectory and kind of have a guess where this object is outside of the the field. Yeah, thank you.
Your master control line downstream that's like more complex because the particular function people.
Oh yeah, that's a very good question. So yeah, as I showed, even though I said it's a goal condition manipulation, but it's actually pretty simple because you can see the full like object in the initial and the goal states. And to enable this, more complex, so actually there's no policy in this whole manipulation, it's just actions. So I think in this more complex implementation, I think our model can be used as a visual backbone that provide you with some extra information for correspondence, and you can on top of it train a like imitation learning policy that can help you manipulate like following some demonstrations. Yeah. Thank you.
Yeah.
Oh, do you want me to connect through HDMI or is this okay? Okay, cool. Cool. So, hi everyone, I'm Leon and I'm a PhD student at Penn. And I'll be presenting our work on vision-based contact localization without touch or force sensing. This work is part of the main conference, so I hope to see you either at the workshop or at our main poster session on Thursday. So to begin, contact is the primary means by which we manipulate our surroundings, and it captures useful information throughout all stages of manipulation tasks. So take, for example, this task of inserting a book into this slot. We need to construct a plan that involves deciding when and where to make contact between the book and the shelf. And to do so efficiently, we'll probably make use of past experiences or even watching other people doing similar tasks. To robustly execute this task, we perceive contact in order to inform our estimates of the environment, as well as our reactive control strategies. So contact is essential to manipulation. And of course, perceiving contact has been of great interest to the robotic manipulation community for some time. But prior work has primarily focused on perceiving contact using tactile and haptic sensing. With new developments in visual tactile sensors, we can now get incredible amounts of information of contacts made on the robot. But for many tasks, contact between a grasped object and the environment is equally important. But to perceive these extrinsic contacts, these sensors are limited by their locality and require stronger assumptions to resolve ambiguities, such as knowing the object geometry and pose, or redefining the contact configurations with tight coupling with information gathering motions. So we're going to take a slightly different approach and make use of vision sensing to give us a more global information about the scene. And specifically, we're going to assume we're given a sequence of RGBD images from a single viewpoint. And in each image, we'd like to locate the extrinsic contact locations. And we're not going to make assumptions about the objects, its properties, or the potential contact interactions between them. So from vision, one viable approach would be to estimate the poses and geometry of objects. But to capture the binary nature of contact, capturing the binary nature of contact can be difficult with these continuously valued estimates. So instead, we're going to take a more model-free approach and directly learn to predict contact from images. And we're going to train in sim and transfer directly to real. I'm going to skip directly to our results, but first I'm going to have to explain some visual notation that's used throughout the presentation. So first, these pink crosses denote our annotated contacts. And this blue-green splotches kind of our predicted contact probability map. And these green dots denote our predicted contact locations. So our approach, we call im to contact, works across a wide variety of different contact interactions that include different configurations, such as point and line, different contact modes, such as sticking and sliding, and simultaneously can localize contact interactions between multiple collision pairs. To achieve this, our method leverages simulation to generate a diverse data set of contact interactions by episodically randomizing the objects in the scene and the robot motions. And we'll repeat this over a large number of episodes and get labels by projecting the ground truth contact locations into the image. With this data set, we can now train a standard unit to take in an input image at each time step, supervise its output on a pixel-wise BCE loss to get a output contact probability map, which for evaluation purposes, we can further reduce to a small set of predicted contact locations using an adapted non-maximum suppression algorithm. And then after training these models, we'll transfer directly to real zero shot, where we've collected and manually annotated 30 episodes or about 13 minutes worth of teleoperated robot interactions with a wide variety of household objects. In developing our approach, we investigated 3 possible improvements over a naive baseline, which simply takes in a single depth image at each time step. Firstly, we know that the relevant visual region to predict extrinsic contact is concentrated near the grass object. So we're going to apply a conservatively sized crop centered about the gripper location to reduce any effects of sim to real gap. And to provide some initial evidence of how this helps, we visualize the predictions of our fully combined approach along with the ablation of cropping. And you'll see that our ablation of crop continuously produces false positives around the noisy and missing depth pixels at the top of the can, whereas our combined approach does not suffer from such sensitivity. Secondly, from a single depth image, it can be difficult to disambiguate near from true contact, especially in cluttered scenes. However, we know that contact often induces motion in the environment, which we attempt to capture by concatenating flow with the depth input. And you'll see that our ablation of flow continuously produces false predictions on a nearby foreground can, whereas our combined approach is actually able to identify the true contact between the background can. And finally, and along similar lines, from a single depth image, it can be difficult to disambiguate the grass object from the environment geometry. And so we will make some light assumption that the episode begins with a unincluded view of the grass object. And we'll use this as a vague hint at the grass object geometry by encoding it separately from the current depth image and concatenating these two at the bottleneck of the unit. And you'll see our ablation of this object reference frame, as we call it, produces many irrelevant predictions between the environment geometries, whereas our full method is able to properly localize the occluded contact. To evaluate which of these components actually consistently led to improvements, we quantitatively evaluate each of our ablations along with the naive baseline, which we call unit depth. We compute precision and recall metrics on both unseen simulation and real data by using a Hungarian matching algorithm with some distance-based cutoff. And you'll see that on simulation, most of these methods perform quite similarly. But for the methods that do not include cropping, they drastically deteriorate once transferred to real. And for our remaining two ablations, we find that object reference frame does have a noticeable impact on the performance, whereas we don't notice a significant difference when ablating flow. But for future work, we definitely plan to further investigate how we can actually realize the motion and tactile information in order to make the crucial distinction between near and true contact for our method. So I'll jump back to our final or our main approach. And when transferring this directly to significantly out of distribution settings, we find that predictions are actually still reasonable. And we're particularly excited about these results as we believe there's strong potential using these extrinsic contact estimates from human demonstrations to accelerate or enable new robotic manipulation capabilities on tasks such as object rearrangement, tool use, and assembly. And in the near term, we've been working to improve the contact perception capabilities of our system. And we find that training contact localization jointly with geometry prediction actually improves contact localization and can also provide us estimates of contact normals, which are the blue arrows, which give us directions to make and break contact or to slide locally along a surface. So to summarize, we propose a method that can localize contact without explicit assumptions on objects, their properties, or the potential contact interactions between them. This method exhibits promising generalization to out of distribution settings, and we're currently working to improve localization, add new contact-based features, and importantly, and something I'd love to discuss with you all, demonstrate the downstream utility for robot learning. Please check out our website and paper for the details. Thank you.
I have a couple of quick questions, please.
So now it's a pure vision problem.
Yeah, that's right.
What do you think? How do you use this for some manipulation tasks?
We think that this is particularly with the new developments where we provide contact locations and some geometry features. I won't be able to go into the details now, but I'd love to talk to you after. We think this is a promising representation for like reinforcement learning. That's more that might be more efficient.
Okay, let's meet at 4 o'clock again. We have a couple of more talks pending.
Yep, break for coffee and we'll meet at 4.